All right, section 9.4 and 9.5. We're going to do two lessons today, 9.4 and 9.5. 9.4 is on compositions and isometries. So an isometry is a transformation that preserves distance or length. So it's a shorthand notation for any transformation that keeps the figure the same size with all the same angles. So any translation, reflection, or rotation. So all three of the things we learned today so far in this chapter are isometries. So let's look down below and see which letters in this lowercase alphabet could be transformations of each other. Name what type of transformation this is. So let's look at first. Let's look at B and D. Can we use a reflection, a rotation, or a translation to describe it? Okay.
Reflection.
A reflection. So a reflection here. Take a look at the rest of them and see if you can find any other ones. So another one, right? What about N and U? How could we get from N to U? A rotation, very good. So a rotation. Now let's look at one more. What if I look at B and P? P and P, will a reflection work?
Yeah.
Not quite. Will a rotation work?
No.
Let's see. What if I took B and I rotated it counterclockwise, end up like this, right? And then I wasn't done there, and then I reflected it across that line, I end up with P. So to get from B to P, we'd have to do a composition of rigid motions. So a composition of a reflection and a rotation. So composition is a combination of transformations. Yes, you.
What about P and Q?
P and Q will work too. That's a reflection. And then D and P could be a rotation. All right. Now that we have those, let's look at this example down below. So we want to match the composition with the diagram. So we have three different descriptions, and then we have three different pictures. So the solid figure is our starting point. So we're going to go to solid. That is our first, where we're starting. Then we're going to go to the dashed. That's the image of the solid figure. And then the image of the dashed figure is going to be the dotted. That's our third. That's our ending spot. All right. So what I'd like you to do is, for these descriptions down below, write A, B, or C as to which one describes each of those circumstances. All right, here we go. Let's see how we did. So let's look at this first one. To get from this solid to the dashed in A, that's a translation. And then to get from the dashed to the dotted, we're going to have to reflect it. So translate parallel to line M, and reflect across M. That's going to be A right there. This one, let's see what we're doing here. So I'm starting here. I'm going to rotate about point P. And then that's not a reflection. Look at how these guys work. Right? So this little part of it is right here. It's not a reflection. It's actually going to be a translation. Remember that translation just slides it on over, slides it from one to the other. So that's going to be a rotation and then a translation. So let's see which one that is. We'll rotate about point P and translate perpendicular to line A. There's our V. And the last one must be C. So let's go ahead and look at this. We're going to reflect across M and then rotate about point P. All right, moving forward. New notation. So a new way to denote function notations, because what we're doing with transformations is simply a function, right? An operation that we're performing on either a point, an image, a letter, a shape, anything like that. So the most common mistake people make in this particular lesson is this notation. We're going to go right to left. So this is the first operation we perform. And then this is going to be the second. We go right to left, or inside out. So just like we do something in function notation, f of x, and if I had two functions, g of x, one way to write f of g of x would be f of x, g of x. Okay? So this would say we're going to perform the g of x function first, and then we're going to take what we get from there and plug it into the f of x one. So we go right to left. So same sort of notation, just written two different ways. Okay? So for the purposes of this particular unit and lesson, just remember when you see this, we're going to go from right to left. Okay? So first thing I want to do, reflect across L. So J to L, right there. And then I want to go the same distance from the line in the opposite direction. So J will look like this, pointing in the other direction. And then I'm going to reflect it across line M. We're going to reflect it back all the way there. And the same distance, right? Which preserves the distance from our line of reflection. The other direction. So where that one ends up all the way back over here. And our J is back right way again. So we reflected this J all the way across line L and then back across line M. So one of the most common compositions is the glide reflection. The glide reflection is a combination or a composition of a reflection and a translation. We have a translation and a reflection together. These ones we typically do the translation first and the reflection, but it turns out you're going to end up in the same spot regardless of which one you perform first. So let's go ahead and graph triangle text first. Let's make sure we go ahead and label our points. All right. So remember, we're going to go right to left. And let's graph the intermediate one first. So I'm going to go and perform the translation. So that translation rule, remember, tells me I go 0 left and right, and then 5 down. So I'm going to drop each of these down 5. So T is going to go down 1, 2, 3, 4, 5. X down 1, 2, 3, 4, 5. I'm going to bring E down as well. But I'm not finished there. Since it is a composition, right, we're going to need to do the reflection as well. So we'll take care of the reflection next. So the reflection, x equals 0 is the equation of the line for the y-axis, right? We're going to reflect it over this vertical line. So remember, I can count the distance from the line and go perpendicular in the opposite direction. So E here, here's my final E prime, and then T. There is T prime, and X, 1, 2, 1, 2. There's X prime. And I always color in my last image, the image where I ended up. Color that in. And that's what we wanted to find. So that's a glide reflection, a composition of a translation and then reflecting it back over that line.
He started it already.
All right, so we're going to continue on with 9.5, congruence transformations. So it turns out all the stuff we learned in chapter 4 about proving polygons and triangles congruent, the side angle side, all that kind of stuff, there's an easier way. Since isometries preserve distance and angle measures, if I can show the composition of rigid motions can land one shape on top of the other, then I can show that those two shapes are in fact congruent. So for this first one, we have A, B, C, D. So let's see if I move this and I end up right on top of Hij, K. Okay? So a translation is probably the first place to look. Can I translate one of these polygons directly on top of the other? So if I move A, B, C, D over to the right, so going in the positive direction, and then drop it down, does it match perfectly with this one?
Yes.
If it does, then those two shapes are congruent. So instead of proving congruence, I can say that A, B, C, D is congruent to H, I, J, K by simply a translation. How many did I have to go to the right? Over 1, 2, 3, 4, 5, 6. We're going over 6 to the right, so that's positive to the right. And then down 1, 2, 3, 4, 5. Negative 5. My congruence transformation is done. I've shown those two figures, those two parallelograms as they turn out, to be congruent by simply translating one on top of the other. So this next one's a little bit tricky. I want to show that UVW is congruent to this triangle down here. So notice, I'm going to first check to see, will the translation work? Can I just slide this guy right on top of the other?
No.
So if I go over and then down, sadly, it doesn't match up quite perfectly. So the next part I look is, I have two other options, a rotation and a reflection. I always start with the reflection because they tend to be a little bit easier to match up and accomplish. So let's first see what happens when I slide this over and then reflect it down. Let's see about a glide reflection. So I'm going to move this over. 1, 2, 3, 4, 5, 6. Move this over 1, 2, 3, 4, 5, 6. And then over 1, 2, 3, 4, 5, 6. So what I did is translated that over so it lines up a couple of the vertices. Okay. So I translated that over. I went negative how many? 1, 2, 3, 4, 5, 6. Negative 6. Up and down 0. All right, next, I'm going to go ahead and reflect this across the x-axis. Fill this guy right here. The equation of the x-axis, y equals 0. So this is 1 here, 1 there. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3. 1, 2, 3. Notice it lands perfectly on top with a reflection. So this is a composition. Of a translation and a reflection. So we can show that triangle UVW is congruent to triangle. This is where it's a little bit tricky. We have to match up the vertices. Right? So U, when we slid that over, was right here. V was right there, and W. So U goes with the Q over here. And then the V goes with N down here. And then the W goes with N. So we've shown that these two triangles are congruent to a glide reflection, the composition of a translation and a reflection. Now you guys try. All right, so the last example here, let's go ahead and take a look at this. How can I get from triangle NAV to BCY? Just looking at this, I see that they don't quite line up, so a translation is not going to do the job. So I'm going to go ahead and look to see if I can slide it over to match up some of the vertices and then reflect it. So let's first see what happens when take this guy and slide it over. Okay. Now if we look, I can go ahead and then reflect it over the x-axis. So let's go ahead and label these. Oh no. There's my NAV. So to get from to NAV to BCY, I'm going to first translate. And I'm going up and down 0. I'm going to go over 1, 2, 3, 4, 5. To the left. And then I'm going to reflect it across this horizontal line here, which we can write as y equals 0. Right? Y equals 0 is the equational line for the x-axis. Thank you for watching my video.
Wait, no.